Hello and welcome back to the BioRT-HBV modeling video series. This is the third video on carbonate weathering. And in this video, I'm going to show you how to run the BioRT model in a Linux system using our carbonate reaction network that we set up in the previous video. I'll then go over the folder setup and show you how all of the input and output files are organized. We'll run the model and then we'll look at the output file and some plots of the model results. So a quick review from the last video. In order to set up a weathering reaction in BioRT, we need to amend the chem file where we list out all of our species and reactions, the CI/NI file where we have all the initial conditions and the dependency factors, and the precip chem files for the precipitation chemistry. Now, in order to run BioRT in our Linux system, we need to make sure that all of our files are in the right locations. So in the main folder where you've compiled the BioRT executable, you also need an input folder and an output folder. And so within the input folder is where you'll have separate folders for different simulations or different cases. And each of these folders needs a unique name, and you want to make sure that that name is informative so that you know what the simulation is. And so in the example that I'll show you today, I'm naming my case folder Carbonate Demo Base Case. And just note that you should not have any spaces or punctuation in your folder name. And so within that case folder, you'll have all of your input files for running BioRT. And so these include the chem file, the CI/NI file, CDBS file, soil file, precip chem file, and numerical experiment precip chem file. You'll also need the results and the parameter files from the associated HBV light simulation, including the results file, the numerical experiment results file, and the parameter file. And you don't need anything in the output folder, but this is where the results files will save once you run the model. Okay, now to run the model, I'll go over the basic commands and then demonstrate this in the Linux system. So first, you need to navigate to the main folder where you have that BioRT executable and the input and output folders. And so you can do this by using the Linux command cd to change the directory until you get to your main folder. So once you're there, you can check that you're in the right folder with the command ls, and that will list out all the contents of that directory. And so the command to run the model is /BioRT space case name. And so here in my example at the bottom, the case name is Carbonate Demo _ base case. So I've typed in this whole command at the bottom, and then I hit enter to run the model. And so I'll demonstrate this in the Linux system now so that you can see what that all looks like. Okay, so I'm in the terminal, and I'll first navigate to my main folder by going to my work directory, and then my main folder is called BioRT Demo. So I'll navigate there with the cd commands. And then to make sure I'm in the right place, I'll list out all the contents of that directory. And I see that I have the BioRT executable, the input folder, and the output folder. And so I guess just to show you what's in the input folder, we can go in there and list out the case that I have there. So we can see that the case I have is called Carbonate Demo _ base case. And so I'm in the right place. And so you can navigate back to that folder by doing cd space .. and that'll go up a level. So I'm back in the BioRT demo folder, and this is where I can run the model command line with /BioRT space Carbonate Demo _ base case. And this needs to match exactly what is in that input folder. So I'll hit enter, and the simulation will run. All right, so once you see the lines that say the simulation and the numerical experiment have succeeded, that means that your results files have saved in the output folder. So I'm gonna switch to the tab with all of my folders and files, and we can go and look into the output folder, and we can see that those results and numerical experiment numerical experiment results files have been saved. All right, so as we saw in the terminal, once we see the lines HBV BioRT, case name, simulation, and numerical experiment have succeeded, that means that our output files have been generated. And so just to kind of break this down a little bit, the name of the results files follows this format where you have the case name that you defined for your folder, _results _ date time. And that's the same thing for the results file and then the numerical experiment results file. The date time format follows the year, month, day, hour, minute. So in this example, if you have 23/07/01/09/00, that date time format corresponds to the 1st of July 2023 at 9 a.m. All right, so the output file includes time series of the primary species concentrations in snow, surface water, shallow zone water, deep zone water, and the river or stream water. Secondary species concentrations in the shallow zone, deep zone, and the river/stream, and then the reaction rates in the shallow zone and the deep zone. So this is a screenshot of some results where the first column is always the date or time of the simulation. And you can see that each column includes a header, the first line, and then the units corresponding to that header in the second line. And so then it starts the time series of all of your simulation results. And so looking at the column names from left to right, we have the concentrations of primary species in the snow and surface, followed by concentrations of primary and secondary species in the upper or shallow zone, the lower or deep zone, and then the river. And then lastly, all the way to the right-hand side of the results file, you'll have the reaction rates in the upper or shallow zone and then the lower or deeper zone. And so you can download this file and then plot out the results in whatever software or language you prefer. And so now we're going to look at some results from this specific simulation. So here I've plotted the time series for dissolved inorganic carbon concentrations in the stream, shallow zone, and deep zone, where dissolved inorganic carbon, or DIC, is just the sum of those three aqueous carbonate species: carbonate, bicarbonate, and carbon dioxide. And below that, I have the reaction rates for carbonate weathering in the shallow zone in the lighter color and in the deep zone in the darker color. And so the rates are in moles of calcium carbonate per meter squared per day. And so if we focus on the top figure, we can see that the concentration of DIC is consistently higher in the deep zone with this dark color compared to the shallow zone, this light color that's almost zero. And so this makes sense since we started with more solid calcium carbonate in the deep zone to reflect where the calcite bedrock is in our catchment. And so more calcite is available in the deep zone, and so more calcite is dissolving to produce calcium ions and carbonate ions. Now, coming down to the bottom and looking at the reaction rates, we can also see that the deep zone rates are generally higher than the shallow zone rates, meaning that the calcium carbonate is dissolving more consistently in the deep zone. And in contrast, the shallow zone rates are often near zero, indicating equilibrium. And so when the shallow zone rates increase or decrease from zero, this means that the reaction was driven out of equilibrium to dissolve or precipitate the calcium carbonate. So next, I've plotted out the time series for the hydrology from the HBV light simulation with the total Q or stream flow, and then the component flows from the surface, the shallow zone, and the deep zone. And so we can see that the deep zone flow is pretty high and constant throughout the year, whereas the shallow zone flow peaks with peaks in total discharge, likely responding to inputs of precipitation and snowmelt. And so the contribution of the surface flow is pretty minimal, so we won't discuss that component very much. But now moving to the bottom and looking at the stream concentrations, this line basically uses the deep zone concentrations as a baseline and then peaks downward throughout the simulation towards the shallow zone concentrations. However, they never fully reach the shallow zone line. This demonstrates how the stream chemistry is controlled by the different hydrologic flow paths that contribute water and chemistry to the stream, as the stream is generally dominated by deep zone flow but gets additional inputs of water from the shallow zone with those sporadic peaks throughout the year. And as a result, the stream concentrations are generally high when deep zone flow is dominating, but the concentrations are diluted by the shallow zone water when the shallow flow contributes to the stream. And so those are some basic figures that you can plot to look at your model results, but you can of course explore other results as much as you would like. So that's all I have for this video. Thank you very much for watching. In the next video, we'll go over how to change a model parameter and how that can affect your results. Thanks.